The next kind of proof that we are going to look at in class is the following kind of things. So we're proving a fact about sum. The challenge with these is directly proving them, and we actually saw this sum fact back when we did sums in series. Directly proving them becomes really difficult. But there is a clever technique we can use called proof by induction. So we are going to spend our time doing a proof by induction. Now there's 3 stages to any proof by induction. And the first stage is to talk about when n equals 1. So we want to find out when n equals 1, what happens? Well, in that case, we are summing from 1 to 1 of the r squareds. Now, what does that look like? Well, the sum from 1 to 1 of r squared is just 1 squared. There's no 2 squared because we're just summing up to 1. So 1 squared, which is just 1. So we call this the left-hand side and the right-hand side. What does the right-hand side say? Well, it says all of this. So we're doing a sixth times 1 times 1 plus 1 times 2 times 1 plus 1. So I'm just putting 1 in up into this equation here. Doing that, well, 1 plus 1 is 2, times it by 3, so that's 6 times a sixth, which equals 1. So that's a relief. If we're trying to prove this thing, it works when n equals 1. So that we can write that down. So left-hand side equals right-hand side. So true for n equals 1. Now, that's all good and well. We could go through, we could do a whole set of cases. That's not going to be very helpful. What we could do, though, is if we can show that when n is true for some case, then it will be true for the next case. That would allow us to then unlock every single case. Because if we know 1's true, and we know what a case being true makes the next one true, then 1 would show that 2 is true, 2 would show that 3 is true, 3 would show that 4 is true, and so on. It would actually show it's true for every single case. So when n equals k, assume true. So that is the sum from n equals 1 to k of r squared is equal to 1/6 of k plus 1, 2k plus 1. So I'm just recopying basically what the original formula was for that one. We're assuming it works when n equals k. Now we need to look at for n equals k plus 1. And we need to show that if this one is true, then the next one automatically becomes true. If we can do that, we've proved our fact. So here goes. For n equals k, well, we're taking that left-hand side. And we're doing the sum from n equals 1 to k plus 1 of r squared. So that's adding up all the square numbers between 1 and whatever k plus 1 is. But that's the same as adding up all the square numbers from 1 up to k, and then adding on our last term. Now, what is our last term? Well, it was k plus 1 all squared. So it's that thing. Great. Might not look like we're getting anywhere, but we've seen this before. We saw this term in what we assumed to be true. So we can plug that in. So we have 1/6 k plus 1, 2k plus 1, plus this term here, which is our k plus 1 all squared. Well, with that in the bank, it's a lot of algebra ahead of us. We need to simplify this. At the end, what we're looking for is the whole statement that we have here, but instead of k's in here, we want k plus 1's. So we're going to aim for, and this can be helpful because it gives us a kind of sense of where we're trying to get to. We're aiming for 1/6 k plus 1. Putting k plus 1 instead of k there gives k plus 1 plus another 1, so k plus 2. And putting k plus 1 in here gives us 2k. Doubling the 1 as well gets 2 plus 1, so plus 3. So this is what we're kind of aiming for with the algebra that we're sorting out. So it's helpful to have that in the back of our minds as we go. First thing I would do here is factorize out the sixth and a k plus 1. Always good to put your fractions at the front. That's a k. a 2k plus 1 plus, and from this term, we're taking out a 6. But there wasn't a 6 to take out, so we need an extra 6 to come in, because 6 times the 6 will cancel out and give us just the 1 there. And we're left with one of our k plus 1. So k plus 1 squared, one of them's over here, one of them is here. Now, we can simplify this bit in the brackets. So that's going to be 1/6 k plus 1. Expanding out, we've got 2k squared plus k plus 6k plus 6. Simplifying by a step, we've got 6k plus 1, 2k squared plus 7k plus 6. 6k plus 1. Now I want to factorize this bit. You can either do that using splitting the middle term method, or you can think what the aim is and work backwards. I would highly recommend that approach because it will save you a lot of time in your exam. I'm going to try k plus 2, 2k plus 3. Now I say, looking at the aim, I've literally copied it, but it is worth checking. So 2k times k is 2k squared, 2k times 2k is 4k, plus another 3k. Yep, that gives us our 7k. 2 times the 3 gives us our 6. So this equals the right-hand side that we expected. Because that was what we wrote down as our aim, that's what you get up here if you put k plus 1 in instead of k. So, what have we managed to do? Well, we want to summarize with a little statement. Our statement here is really important, and it always looks very similar as, and I'm going to say the conjecture because it's quicker than writing the original thing. So as the conjecture is true for n equals 1 and n equals k true implies n equals k plus 1 true. Then the conjecture is true for all n greater than or equal to 1. Because we started at 1, we showed that if one case is true, then the next one is true. So that means this being true at 1 makes 2 true. 2 being true makes 3 true. 3 true makes 4 true. 4 being true makes 5 true. 5 being true makes 6 true. And we keep going. And we're getting all the n's. We don't prove it for all n, but all the ones bigger than 1, it will work. And our proof is complete.